And our next speaker will be Mario Carneiro. He's the most active and laborious user of MetaMath. So we switch the formalization environment now to MetaMath. And Mario will show us these ideas about formalizing two elements from this Frey-Videix 100 theorem list, namely the Dirichlet theorem and the prime number theorem, which is, I believe, more okay. We'll switch into editor. Similar to chats. Sure.
Okay, so yeah, I'm going to talk about the formalization of the prime number theorem and Dirichlet's theorem in MetaMath. So first I'll start with what MetaMath is. It is a formalization system like Nizar, like Israel, and it has a very simple specification. This is one of the design targets for MetaMath. Is it has a two-page specification. There are verifiers which exist in very few lines of code, and it also can verify very quickly. And I'll talk more about that in the beginning. There are several proof assistants for it, and I worked these two projects mainly in the proof assistant called MMJ2. Tomorrow, I'm going to talk a little bit about the theoretical underpinnings for how MetaMath in general can work. So we'll come to that. The main database is called set.mm. There's 29 megabytes of library data there, 28,000 proofs. So here's a statement of the prime number theorem, and this is the way it shows on the MetaMath website. I have there at the bottom a web page you can go to. Just change this PNT for any of the other theorem labels, and then you can see what all these look like there. And it will show the complete proofs back down to ZFC axioms. So some notation notes. Pi is the prime pi function. There's an underline under the pi in order to distinguish it from the mathematical constant. The interval from 1 to infinity, because the logarithm has a goes to infinity. When you divide by the logarithm, it goes to 0. So we avoid that, and then this is just saying that the limit of it goes to 1. So the actual statement of the theorem is quite concise and hopefully means what you believe it to mean. So this theorem was first conjectured by Dijon in 1797. The first proof of it was done by Jacques Hadamard and Charles-Jean de Laval-Poisson in 1896. These, I believe, were independent proofs. Later on, there was this elementary proof discovered by Erdős and Selberg, and their relationship during this proof was not very nice, but in 1949 they came up with these proofs which both rely on the Selberg symmetry function, which I'll talk about later. The first formal proof was done by Jeremy Avogadro, who I hope to be working with soon. The end of this year, I'll be starting at Carnegie Mellon University, so I'll get to talk with him about that. And this was done in Isabelle. And there was another formal proof done by John Harrison in Hull Light, and I believe John Harrison will be coming here later in the conference. And so he did the complex analysis proof. Avogadro did Selberg's proof, and I also did Selberg's proof. So my formalization is quite similar to his, although I did not use his actual Isabelle code. I consulted the same informal source as he did. So in a lot of ways they can be compared in this way. So here's Dirichlet's theorem. This one doesn't use as many non-standard abbreviations. Just says if n is a natural number, a is an integer, and they're relatively prime, then there's an infinite number of prime numbers which are equivalent to a mod n. So nothing fancy going on here. So this was partially proven by Euler for the case a equals 1, and then Dirichlet came up with the first complete proof, which uses these Dirichlet characters, and so that's a big component of the proof. And John Harrison also wrote the first formal proof of this one in Hall light. So why consider these two? They're both using the same subject. They're dealing with finite sums and asymptotic approximations of these sums. And they're both on the 100 theorems list, so this is 2 more knocked off the list, and currently there's 58 which have been proven out of 100 in Meta. So one of the things I want to mention is that different from Mizar and Isabelle and also Whole Light, MetaMath has a convention that you shouldn't use new definitions unless you need to. So definitions should pay for themselves in terms of how nicely you can state things or how it simplifies the proof. So this is basically a complete list of all of the new or significantly used finite sums. This was not actually defined for this one. We've used finite sums before. And this same notation can also handle infinite sums, which are done on the natural numbers. And there's another definition for even more general sums, but we don't really need that. The prime pi function, the 2 Chebyshev functions called theta and psi, and the von Mengel function, and the Mobius function. So these are all major functions which they all have their own Wikipedia page, and you can read about them, and they all have properties. And we attempt to prove all of the important properties for each of these functions. So that's part of the cost of adding a definition. Is whenever you add a definition, you want to relate it in all the obvious ways to everything which came before. So that means proving a whole bunch of things. So unless you need to, you don't want to. And this allows for a more unified development inside the main library itself, because everything is related to everything else. And there's one way to talk about the prime pi function. Now it's there, and you use that instead of inventing your own new version of the prime pi function.
Margaret, can I so when you define a function, do you have some existence and uniqueness obligations?
So for the most part, a function, except in the very beginning, you can't necessarily do this. But after the initial work, pretty much every definition is a single constant, which is defined. It can be a proper class, and it is defined to equal some closed term.
Okay.
So existence and uniqueness is automatic. There are ways to define things that are uniquely defined because there's an iota builder. There is a way to define in ZF anything which has a unique definition, and then you would be interested in proving that it is unique in order to use it. Although you can, just by writing down the expression, you know already that it's unique. It's just that it's going to value to something useless if you don't prove it.
So the existence comes out just by syntax, basically.
Yeah,
By the fact
if
that
you
you
define a ZFC term, it's a class.
Mm.
It's some actual class. It might not be a set, but it's a class.
So the iota of empty set is
The iota of the empty set is the empty set.
okay.
The iota of something not unique is the empty set.
Okay.
So it's always going to exist.
Okay.
And in fact, the iota is always a set also.
A detail. On the previous slide, you had the definition of the Mobius function.
Yeah.
The 2 vertical lines, is it does mean divides or that divides and no high power divides?
So this isn't actually the definition of the Mobius, this is the definition of the Mobius function for square-free integers. In the actual code, it'll say, if it's square-free, then it's this thing, otherwise it's 0. As for what this means, this is taking -1 to the power of the number of primes that divide it. So if it's a square-free integer, you count up how many primes there are, and the hash is counting up how many of those primes are there.
But if n is not, if n contains a square factor, then the value of the function is
Yeah, if there's actually an if around this whole thing. So if it's square free, then it's this. Otherwise, it's 0. So yeah, for brevity, I didn't want to put the full definition.
And for the von Mangold function, how do you extend it to?
That one as well. In that one, I asked, is it in fact of the form p to the alpha, where p is a prime? And if so, that prime is uniquely defined, and I use that uniquely defined p in here. So here is the way the definition. This isn't actually the definition either, because the definition is a little bit harder to read than this. But this is the definitional theorem for the group of Dirichlet characters. So this also allows you to see a little bit of how groups are defined. This is a structure. So this is the group of Dirichlet characters with so the base, which in Mozart is called carrier, is D, which is this, the set of all monoid homomorphisms of the multiplicative group of Z by NZ, where N is a fixed. So N is, even here, it's a parameter for the whole group. So this gives you a selection of groups indexed by N. And so for that N, you have the structure of Z by NZ, and then that structure has a multiplicative group, or actually multiplicative monoid. And so the monoid homomorphisms from that to the complex numbers as a structure. So this is all very, this is using the structure formalism, which is done in MetaMath to create a new structure from old structures. And so the monoid homomorphisms, which have also been extended to have value 0 at everything which isn't a unit. So this is using some very high concepts from how Z by NZ is supposed to work, but it amounts to the same definition as some of the others, and we proved that it has the same definition as some of the others. That's, again, one of the things which you want to do whenever you introduce a new concept. You prove that it has all the properties that you expect it to have.
So the term mode group is not particular group of some ring which comes afterwards.
Yes, so Z is a ring, and multiplicative group, all it does is a ring has a base and an addition and a multiplication. The multiplicative group function here will take any structure which has these 3 components, and it just takes the multiplication and puts it on top of the addition. So it gives you the group of multiplication as the group operation. So it allows you to treat the multiplicative group of a ring. You can use the ring as itself if you want to treat the additive group, because it's already in the right slot. But if you want to use it as multiplication, then you just replace the multiplication with the addition, and that's what this mole group function does. Is that all right?
What was the capital N? Last question for now.
Which capital N?
And the top line of the box.
So N is, so these 2 which start with the blue feet, these are the assumptions. So I start with the assumption that N is a natural number, and then I'm giving the definition of G based on that. And so everything which starts with G equals, Z equals, these are all abbreviations. Or at least this is the way which MetaMath does abbreviations. It's saying that given that G is any class which happens to be equal to that thing, and there's really only one thing which could possibly be equal to that, it allows me to use G in all these locations, and then when I substitute G with D sure of N there, it will just go in here. So that way I have the abbreviation without needing to have some fundamental structure for abbreviations or something. And in this case, This is also an abbreviation, but I'm putting it in a hypothesis because later on I can prove that this is in fact the base set of G, but that would be a recursive self-referencing definition, so I can't use that initially. But later on I do use it, so it's useful to have non-identity abbreviations like that. Temporary definitions, well, I kind of mentioned that a little bit here, but so R, so this is one of the statements which I have to use during the prime number theorem, and I make use of this R, and this is the residual of the Chebyshev psi function, and so when you look at informal proofs of the prime number theorem, they use this R function all the time, but I don't really want to define this like for real and give it a name, because these names have to be globally unique, which is sometimes annoying to work with. I don't have to worry that R is globally unique because R is a variable. So I introduce a hypothesis which says that R is equal to the residual, and then I use this hypothesis through 20 theorems in a row. And I just keep referring back to the same hypothesis. When I'm done with it, I prove something that doesn't involve R. I replace that with reflexivity, and then the hypothesis goes away, and I'm done. And I never had to define what this thing is, a new global definition. Okay, so here's some comparison between, so this is Steve proving Dirichlet, me proving prime number theorem, John Harrison proving Dirichlet, and Avogadro proving prime number theorem. So I didn't look at Harrison proving the prime number theorem because he uses a completely different proof, so it doesn't make that much sense. Dirichlet uses, there are 55 theorems which come out of the development. So these are new things. There were a lot of theorems obviously in the library already. I'm not counting those, but there were 55 new theorems which were added in order to support Dirichlet's theorem. So that's none of this one. And the prime number theorem is 83. So the de Bruijn factors are higher than I would have liked them to be. The reasons for this are, I actually had to estimate these de Bruijn factors because I didn't have the LaTeX source for the informal proof. But these are proofs, they're not proof scripts. This is a difference between MetaMath and the others, is that you don't store the way you derived the proof. You store the proof itself, which means actual theorem applications exist. One of the consequences of it is that verification is not even fun. There's a new verifier can verify all 28,000 theorems in half a second. So that is just phenomenally faster than anything that you can get in any of the other programs. So that's one of the big differences. So I'm not going to spend too much time on this, remaining short, but here's some highlights. This is Selberg's theorem, all 8 forms of it. So there's tons of versions of this single theorem, which are all called Selberg's theorem. This is an example of one of the innermost complicated internal lemmas. So you can see how all of the hypotheses are stacking up. Half of these are hypotheses, the other half are abbreviations. And so you're trying to prove something, and you're using all of these things which came, which are building up during the proof. And this is probably like a 100-step theorem, and there's about 20 of these, and these make up the main part of the prime number theorem. This is an interesting theorem about relating any finite sum to its integral. So you can find the derivative of a function, and then you automatically know what the integral of in the other direction is, and that allows you to relate them. And this is one from in the middle of the Dirichlet experiment. So finding for the Dirichlet for sums over a Dirichlet character times mu or times lambda. And I'm also going to show you just a little bit of how these were done. So this is an example of that same inner theorem. So this is how I would actually type it. And you can, this is from MMJ2. So I can type in a formula, and then it gives me back the sub-goals which I need to satisfy. And so I would prove, that this is less than something, and something is less than this other thing, and that's what I was trying to prove at the beginning. So this is proving that less than is transitive. That's my first step in the proof, or right, last step in the
So
proof.
does the unification step basically, it tries to get the current goal and match it against the theorem that you typed? Or?
So it will, I told it that I wanted this lettered theorem. I wanted to use that, and then it tells me what else we need to prove. This actually has 5 assumptions, but it was able to find the first 2 earlier in here. And I don't actually have to prove this one in here. Once I tell it what C1 is going to be, then it will find it also in there. And even if it didn't, it can also prove closure steps automatically. So many of these steps I don't even have to prove.
Like congruence closure steps?
Yeah.
Oh,
So, for example, a while ago, I talked about an arithmetic algorithm, and this is a proof 1,000 plus 2,000 equals 3,000, and now it will prove this automatically. So it just, it finds all the statements and all the proofs it needs in order to prove this. And so this is the output, right? You end up with this thing, which goes inside the MetaMath file. And the MetaMath file can verify that this is correct in, I don't know, a millionth of a second. I didn't have to type much of anything. So it's still reasonable for me to be able to use this for large proofs because of judicious use of automation and being able to type in one step at a time, formulas, and the output looks like the HTML files or something like that.
So how do you then present this in the HTML?
Well,
This sort of
it
huge
looks
things,
basically
they get
like
hidden
this.
somehow, or-
That's what I've been showing during the talk, is the HTML forms of this. Actually, I won't have internet, so I can show you the.
So it's somehow delegated to some extra web page which you don't show basically these sort of automatically generated subproofs or.
Well, I mean, the only thing which really needs to be done from this form of it is just to translate all of these into HTML entities.
Yeah.
And then that's what the
Yeah.
HTML.
But my point is that it's boring. So are you showing it to the users, or you sort of put it into some extra web page which the user doesn't have to look at because
Of
it's
course,
a
the user
lemma?
doesn't have to look at it. Yeah, this is, I mean, you presumably, when you see 1,000 plus 2,000 equals 3,000, you'll believe it. You don't
Yeah.
have to worry
Yeah.
about how it's proven, but if you want to, the HTML page is there,
Okay.
and you can look at, and it will show you all in its gory detail,
Okay.
all this stuff, so, yeah. And, that's it.
Questions?
So I'm curious about how much use of automation you actually made.
So far, so this is MMJ2. MMJ2 can handle arithmetic proofs. I managed to get that into it, and it will also do any, if there are any theorems which you can apply which don't introduce new meta variables and shrink the terms as it's going along, then we have guaranteed convergence, so it will just apply those automatically, except for a blacklist of theorems which do things which I don't think are useful, unless I want them to be done explicitly. So that helps with it. That automatically covers congruence and closure steps. So but that's basically the extent of it at this point. I still have hopes for being able to build a much more elaborate, and I'm actually working on a completely new proof assistant, which will hopefully introduce more Isabelle-like automation functionalities. And there's nothing in principle which stops this from being just as automated as these other systems. It's just that the work needs to be done.
Can I follow up on that? So, if I understand right, all of the formalizations are essentially lines of propositions with some extra information, right? It's sort of Hilbert style.
Yes, this is Hilbert style.
Yeah.
And
like-
I can say, earlier you saw the usage of phi implies in the assumption. So in order to model deduction theory, and I actually had talk about this 2 years ago here, you can use this phi implies as a substitute for deduction, because you can introduce new things by substituting phi for phi and your new assumption, and then you can discharge them in later steps. So you can still do deduction style stuff, even though this is basically a Hilbert system.
Okay, but the way you're using it is more like using natural deduction.
Yeah, I mean, natural deduction is natural, you know.
Yeah.
So people find ways to do it, even in a system like this. It can still be done, and it can be done with minimal overhead. So it still looks really easy to, you know, reading it is not that much different from reading a natural deduction proof, but you don't have to introduce the activity to the system, and so it simplifies the system. And that's a big thing with MetaMath, is you want the system itself to be the kernel, small trusted kernel, to be as simple as possible.
So good, this answers a different question I wanted to ask you later. But but the follow-up I really wanted to ask was, like, if you had to estimate what percentage of lines were generated by automation, and what percentage did you just type in?
That's a tough one. It depends a lot on the subject matter. It might be, 80% is probably a high estimate. Obviously, in a theorem like this, it's basically 0. But I don't find myself doing straight arithmetic proofs all that often. It came up during Bertrand's postulate, and that was what I talked about 2 years ago. But for the most part, you don't need to do these sorts of things, but it is useful to have it when you do.
So in Bizarre or these days, you have type classes in Isabelle, and whatever. The type inference, even the soft type inference, like in Bizarre and the type classes, is a huge thing when you are talking about natural numbers, and by the inclusion mechanism, you know that they are also rational and real and complex, and that therefore a generally stated theorem for complex number will be applicable for natural numbers. So, for example, in Bizarre. So, do you have something like that, or do you do that manually?
The short answer is no. There is a way to do something like that, but it certainly hasn't been implemented. The proof searching will automatically look at all the previous steps in order to see if they apply. So if it sees that you assume that A is a complex number, then it will automatically be able to know that 2A is A plus A. In fact, it'll try to do that anyway, even if you don't tell it A is a complex number. It will just automatically apply. If you say 2A is A plus A, there's no way you could possibly be writing that usefully unless you thought that A was a complex number. So it'll just apply the theorem and then give you back a sub, you have to now prove that A is a complex number. But using these closure, or automatic applications of things, it can find trails to where you want to go, but not all that has been set up. So it's in principle possible, but not.
So when you mentioned the mechanism which sort of applies the inferences which do not introduce new meta variables, that can lead to multiple proof branches, right?
Yeah, so sometimes 2 theorems will apply, and in that case it will actually stop. It won't attempt to even sometimes here, it will often go off on paths,
Yeah,
which,
yeah.
you know,
You,
it's,
you don't want to go.
I've said A plus B equals B plus A, and then it'll say, oh, well, you need to prove that A equals B and B equals A, and wait, no, that's not quite what I meant. So.
So how often does it work?
Huh?
How often does it work?
Well, a lot of the time you're doing conversions. You know, you say 2 times A equals meta variable. And it can't do anything with that because it doesn't know what you want for the meta variable. So you can go in there and you can say, no, apply 2 times here. And then it will say, okay, so you wanted that to be 2 times A equals A plus A. And then it will be able to prove. But you had to know the 2 times. Or else you could type in A plus A for the meta variable. But, I mean, personally, I find it faster to type 2 times because I happen to know that that's the library name. So being able to know the library name does actually improve your speed at being able to work with this stuff. But there's more than one way to do it.
Any more questions? I have a quick question because I'm curious what the drawing factor will be satisfactory for you, because you mentioned that the result that you got for this prime number theorem was not satisfactory. So what would you expect to be if that was
well,
efficient?
I mean, Frick did a measure with this and found numbers like 4. And I've managed to get numbers significantly lower than 4 and numbers higher than it. So it's hard to tell what, you know, there aren't too many projects where it's like you have a actual informal source, you translate it, and now you have a formal source. We just have a bunch of theorems which came from random places, and with this sort of situation, it's really hard to make nice, reliable. This was 2 big projects which used informal sources, so it was easy to translate. But the author was very cavalier about certain assumptions, like the statement about comparing a sum to an integral. He would basically do those in one step. He doesn't even say that that's what he's doing. I don't remember him ever proving that that was a theorem. So I had to go and prove that, and that's part of something which I did, which he didn't do at all, and I'm sure that contributes. So it's things like that which always get you, and I'm pretty sure it's the same in Mizar and everywhere else. It's like the unproven assumption.
Thank you.